All right. Um, so I just want to go through a couple more examples of Laplace's method, in particular on functions that can't be simply decomposed as a product of x and some function phi of t. Just a reminder of what Laplace's method is, okay? That we have some integral, and I'll write it out in a more general form now than I have before. E to the phi of xt dt, okay, as x goes to positive infinity. And we want to essentially find the max of phi x and t, okay, and expand both phi and f around this max, okay, to essentially approximate to leading order by the largest contribution of e to the phi of xt, okay? And in the case where this maximum depends on x, what we need to do is to change coordinates, okay, to try and eliminate this dependence, okay? So we're going to see some examples of that now, okay? So I'm going to start with Stirling's formula and the approach to computing that integral. The gamma function is gamma of x equals the integral from 0 to infinity e to the minus t to the dx minus 1 dt. And we're approximating this as x gets large, okay? So we can rewrite this as e to the minus t, e to the log of t to the x minus 1 dt, or in other words, as 1 over t e to the x log of t minus t dt, okay? So now we have this phi of xt, which has a movable max, as we'll show. So if I take the derivative of phi, now I get minus 1 plus x over t equals 0. T max now is going to equal x in this case, right? So it's a movable max, movable, okay? And so we'd really like to approximate to leading order the integral from x minus epsilon up to x plus epsilon 1 over t e to the x log t minus t dt, okay? Well, phi of xt can be approximated as phi xx plus phi sub t xx t minus x, right? But this vanishes to 0, so that term's going to go away. A half phi sub t t xx t minus x quantity squared plus so on and so on, right? So this can be approximated as x log x minus x minus 1 over 2x t minus x quantity squared plus so on and so on, okay? And f of t then can be approximated as 1 over x, so quite small. Now, if we combine these approximations, we end up with phi of x. The leading order is e to the x log x minus x divided by x, integral from x minus epsilon x plus epsilon e to the minus 1 over 2x t minus x quantity squared dt. Okay. So now if we let epsilon go to 0, okay, basically the little region around there, and we make the following change of variables, t minus x squared over 2x, we can write dt is equal to square root of 2x ds in that case. And that change of variables is going to allow us to just much more simply compute that integral. Okay. Now we could compute that integral otherwise, but often when you have these movable max problems, you're going to want it to perform some sort of change of variables in order to give you a simpler integral. Okay. Moreover, because this term here, right, is going to be dominated by the peak here, right, at x, because x is so large here, okay, then we can extend the integral out to minus infinity up to infinity, because it's not going to significantly change the value of that integral. Okay, so even though we started with an integral from 0 to infinity, we can now extend the approximate integral out to negative infinity. Okay, so this we know how to compute. It's just going to give us a square root of pi. So we can write everything out as square root of 2 pi, x to the minus 1/2, x to the x, e to the minus x, which is Stirling's formula for x goes to infinity. Okay, so this is one of many ways to obtain Stirling's formula, which comes up a lot in physics when you have different ensemble notation in statistical mechanics, many applications of Stirling's formula. It's a good way to approximate also just the factorial function for large values of n in n factorial, right? Because the gamma function is, of course, just the factorial at integer values. Okay, so what do we learn from that? The idea is that you can still handle these problems even if you have a movable max. It's probably going to end up requiring you to make some change of variables in your integral in that case. Okay, one more example, and then we'll be done with Laplace's method for now. Let's start on a fresh page for that. I of x is equal to, say, the integral from 0 to 10 e to the minus x over 1 plus t dt as x goes to positive infinity. Okay. So what's this look like, right? As x increases, slope of this is going to go down more and more. Okay. So as x increases, this is what our integrand looks like as a function of t. Okay. So clearly, as x goes to positive infinity, our largest contribution is from t equals 0, as we can see here, right? Here's t equals 0, right? Away from t equals 0, our integrand is exponentially small, okay? And again, this is why, Laplace's method works so well. We're not throwing away algebraically smaller terms. We're really throwing away exponentially smaller terms. So to leading order, if you can perform an approximation using Laplace's method, it ends up being quite accurate because of this exponential smallness of the other terms that you might think about involving. Okay, of course, your Taylor expanding f, right? So you do have some algebraic dependence on those leftover leading order terms, but at least in terms of how you're truncating this exponential, you're doing it fairly accurately for large values of x. Okay, so so we're going to do the following in this case, and actually split the domain of the integral, okay, and will be revealed why that's helpful. So we have this region that's right around the peak of the function here, okay, the epsilon, and then everything out at larger values of t. Will comprise the other subdomain. Okay, and in particular, we're going to take epsilon to be much larger than 1 over x. 1 over x is going to be very small because x is large. Let's take epsilon to be much larger than that. Okay, but there's still room to take epsilon to be much larger than 1, because assuming x is large, right? You can imagine if x was 100, we could take epsilon to be 0.1, right? And that still lies between these two numbers here. So that's going to mean that our second integral is going to be of order e to the minus epsilon x, right? It's going to be exponentially small, right? Because you have something that is not quite as small as 1 over x. So that means that this whole product term, right, is still going to be much smaller than 1. Okay, so epsilon x is still going to be, much larger than 1 in this case. So that means this whole thing's going to be small. Okay, so we're going to neglect it. Okay, so I can throw out that part now and really just focus on this part. Okay, so now for our first integral, we're going to want to change variables. Okay, because we have this this xt up there. It'll be easier to integrate if we just absorb the x into the t. So remember also we made this assumption. So that'll help us understand what's going to happen with our integral to leading order. So the first integral, we're going to change variables. Okay, xt is going to equal s. So that means dt is going to equal ds over x. Okay, and we'll Taylor expand, okay, in a couple of steps. So I of x to leading order is going to be 1 over x, integral from 0 to x epsilon. Remember, this is still going to be large because epsilon is not on the same order as 1 over x. E to the minus s over 1 plus s over x now, ds. And now comes the Taylor expansion part of f. So we're going to have 1 over x, integral from 0 to x epsilon, e to the minus s, And now we have our symmetric series, n equals 0 up to infinity of minus s to the n, x to the n, okay? And I can also write this as I of x to leading order. Now if I factor out the sum, I have 1 over x to the n plus 1, integral from 0 up to x to the 0 up to x epsilon, minus s to the n, e to the minus s ds, okay? And note, right, because this expansion works as long as s is small enough, right? It's going to be uniform on where s is between 0 and epsilon x, okay? Because that means the argument here, right, is going to be smaller than the denominator down here, okay? So this will converge fine in that case because s over x is going to be less than 1 always, okay? And of course, greater than 0. Okay. Also note that the integral from x epsilon up to infinity of Sn to the e minus s ds is going to be a big O x epsilon to the n e to the minus epsilon x, right? So that's very small. So we're going to replace our upper limit. And now we have an integral that we can compute. So I of x to leading order is going to be the sum from n equals 0 up to infinity, 1 over x to the n plus 1, the integral from 0 up to infinity, minus s to the n, e to the minus s ds, okay? And this integral is just an expression of the factorial, right, by integration by parts. So we have n equals 0 up to infinity, right? I also think of this as sort of a, like the gamma function. So we have minus 1 to the n factorial, divided by x to the n plus 1, okay? So at the end of the day, that that integral gives us this convergent series, and to leading order, it should be fairly accurate. No exponential terms here, right? But you do have these, you know, the successive power series that you get from applying Laplace's method. You could probably do something like integration by parts to get a similar result, but Laplace's method works fine here and then not too many steps. Okay, so hopefully that gives you a good sense of the different types of things you can do with Laplace's method. If you have a small parameter rather than a large parameter, you can always change variables in order to make that small a large parameter and try and turn the handle on Laplace's method that way. If you can't get your integral in a form that's sort of recognizable to Laplace's method, though, you may want to use one of these other techniques that we'll talk about. So on Friday, we're going to introduce method of stationary phase, and then we'll also talk about steepest descent after that, and then we'll be moving on to differential equations. So that's it for today. Again, sorry that I didn't have my pen with me this morning, but hopefully that gives you all a chance just to work through your homework. And maybe these examples will help you find out some loose ends. So I will see you on Friday.